All right, line A6, learning task 4 in the new harmonized models, and it would be learning task 11 in the old non-harmonized models. This is going to be the features of operational amplifiers, or op-amps as we are commonly going to go and call them. And an op-amp is usually represented by this symbol over here, and it's a linear or an analog amplifier. Linear meaning that for any small increase that I get on my input side, I'm going to go and have another small increase that is going to go and happen on my output side. It's going to follow each other. It's not just a discrete where it's going to be on or off, but rather it's going to be how far on and how far off. Originally, these things were used for high gain DC amplification. It is going to be similar to what you have learned about transistors and FETs in that it is going to go and take a small signal but make it larger, but these are going to be much more stabilized than using just a single transistor. There's this whole science that goes around transistors and transistor biasing and balancing and using multiple transistors, etc. What we have inside of an op-amp is we have just got a ton of transistors that are all going to get connected together properly, biased together, properly tuned, and then put out in a tiny, tiny little package. The inside guts actually look like this. And if you take a look at it, what we see over here is we have got just a load of small individual transistors, NPN and PNP type, that are then going to go and get combined. We've got some capacitors, we've got some resistors, and we've got a bunch of, inputs and outputs that we are going to go and have. What I do also note about this is that there is going to be a place where I'm going to bring in positive values of voltage and where I'm going to go and take in negative values of voltage. And ultimately, I'm going to go and control my negative value of voltage to the output over here, or I'm going to go and be able to control my positive value of voltage to the output over here. It's going to be an either or. Either I'm going to be going and sending up some positive value of voltage, a certain magnitude that I'm going to control with that transistor, or I'm going to be sending out a negative, which I'm going to go and control with that. The rest of this over here is really no different on this side here than having a voltmeter on here. And all that voltmeter is going to do is it is going to go and control which one of these on the far output side is going to go and operate. Now, there's a lot more science that's going to be involved than just that section, but it is the basic guts of what these things are designed to go and do. Going back over here, because there's so many transistors inside of there, those transistors are going to go and have cascading amplification. So they're going to go and multiply together. So we're going to go and get ridiculously high values of gain. Gain is just going to be the amount of input that I'm going to go and take in to the amount of output that I'm going to go and get back out. We're going to go and have a gain that is in a lot of cases going to be 200,000, 200K plus. Now this is what the op-amp has dreams of being able to go and do. In practicality, the op-amp is not necessarily going to be able to go and take in, to go and bring out 200,000, because an op-amp itself is not going to go and be a thing that boosts your values of voltage. All it's going to do, as we saw in that previous drawing, is it is going to go and switch voltage in from either the positive or from the negative leads. And they don't show them on this drawing over here. We're going to go jump ahead to one of the previous drawings, then we're going to come back to these drawings over here because we can better explain what's going on. Op-amps do have a power supply, okay? So we're just jumping a little bit ahead over here. They do have a power supply, and that power supply is going to be what we're seeing over here. These ones here, highlighted in green, my VCC and my VEE. VCC stands for voltage collector, VEE is voltage emitter, and these are just common electronic terms that are going to get associated with my positive or with my negative values of voltage. What I have is I have got VCC over here and VEE, which is going to be over here, my negative value of voltage. And if you remember, they all are just controlling. My VCC switches through this transistor, my VEE switches through this transistor over here. And that's all that we're going to see out of here, is that we're going to go and have a switching. This thing is going to be able to go and divert, or this thing is going to go and be able to divert. Once again, if I take a look at my inside guts of this, you'll note that we have got a transistor. What's the voltage drop across the transistor once I get that transistor all the way over to saturation? Well, we're going to go and drop about 0.1, 0.2 of a volt, maybe a little bit more, maybe a little bit less, but we are going to go and have obviously some sort of a voltage drop. voltage drop there, as well as we're going to go and have another voltage drop right over here on this value of resistance. So there is going to be a little less voltage, because by the time I take in those voltage drops, a little less voltage than what's coming in that is going to go and come back out of these over here. Remember how we said before that a op-amp is a dreamer. What it's going to do is it has got this gain. We're going to go and give this thing a gain of 200,000 plus 200K plus that this thing has. That is what this thing wishes that it would be able to do. And given the chance, if I had enough volts that I would go and place onto my voltage supplies over here, it would try to go and do that. However, it's just like the rest of you in that it is going to be limited by what it actually has available. Think about your bank account and think about going out to the bar. If you go to the bar, you might want to be able to go and drop a couple $1,000s at the bar. However, the thing that is limiting you is going to be the $27 that you've got left in your bank account as you're going through your apprenticeship schooling. So you might have these dreams of large values of gain that you might want to go and have out, but in reality, you're going to be limited by what you actually have. That's what happens here to our op-amps. They're going to be limited by what I've got from my voltage supplies. If I've got, 12 volts feeding in, I'm not going to be able to get more than 12 volts out. In fact, I'm going to have a slight bit less because once again, we have those drops on that output voltage run. Okay, let's talk about this input side over here. The input side of our op-amp can be thought of as if it were a very, very small voltmeter across here. You should know a couple of things about voltmeters. Should remember them from first year. Good voltmeter is going to go and have a very, very high value of impedance or resistance. So it's going to be super high value of resistance, which means that the current that is coming into here is going to be tiny. I'm just going to stick a bunch of arrows here pointing down, showing that that is going to be a relatively tiny amount of current that we will have. That tiny amount of current is going to get measured by this. This is then going to go and reference. One of these is going to be tied as my reference. The other one is going to go and be the lead that I'm going to look at. And inside of here, all I want you to imagine this thing is having is that it is going to go and have 3 terminals. Okay? We got 3 little terminals inside of there. Kind of like a 3-way switch. We're going to stick the common on here right now. And I want you to imagine that we've also got inside of this thing just a tiny little elf. Okay? This is not science. This is just how we're going to go and imagine it. He's super tiny. That's our elf in there that we're going to put in. So we've got this little elf. The elf's job is to go and read the voltmeter. And then when he reads the voltmeter, if he sees a positive value of voltage, the elf is then going to go and switch that line to the positive. And when the elf, using his tiny little voltmeter, reads a negative value of voltage, the elf is going to go and switch it to the negative value. How far he's going to drive it into each of those is going to depend upon what we are allowing this thing to go and have for gain. And we'll talk a bit more about that in a minute. Okay, this is going to be what we would refer to as a double-ended supply over here, where I'm going to go and be able to go and supply both positive as well as negative, which is really great because I can go and send a signal positive and then I can send a signal negative. And you can see the benefit of that because we would be able to go and take a tiny little AC signal in and we would be able to go and amplify that into a much larger AC signal out. Why do we want to do it through these? Well, just because in a lot of cases, the signal that's coming in is going to be a weak signal in the microamps. And if I try to run it directly through, that microamp signal is just going to go and get drowned out by the resistance of whatever it is trying to go and feed into. So we take the weak signal over here, we read it, and then we bump it up and we send it out into this output signal. We also sometimes do have a single-sided supply over here. Single-sided supplies are only going to go and have either only a positive or only a negative, and the other side is going to go and attach down to ground. This is that electronic symbol of ground, which is what we refer to as our chassis ground over there. These inputs that are on the front side over here do not have a positive and negative polarity. It's one of the biggest misleading things about the symbol is that the symbol over here does show that we've got this and this. What this is this just tells us about what that input is going to go and do to any signal that comes in. We are going to go and have inverting. That's going to be the negative one. So any sort of negative becomes positive and a positive becomes negative. And we are going to go and have non-inverting. That's just going to become the positive. You can think about these numbers as if this was a negative 200,000 gain. So if I take in a positive value of positive 1 volts, then it is going to go and multiply that through the inverting, the one, this one over here, by a negative 200, and it would want to go and switch out to negative 200 kV. Wouldn't be able to. It would be limited to whatever it can get out of here, but that's what this thing would try to go to. Same with my inverting. Think about that plus over there as just being that this is being a plus 200,000. And so if I've got that plus 200,000 and I bring in a positive value of voltage onto it, what's going to go and happen is that that positive 1 volt is then going to go and get amplified by, well, it wants to go 200,000 times, but in reality it can't, so it's just going to go as high as it can off of the voltage that it is given over here. Okay, that's our basic theory for these ones here. We can go and have these things connected. I don't know where my, this thing just disappeared. Hold on a second. Okay, that was my basic signal there. The video just blanked out. It just does this sometimes with PowerPoint. I don't know why. What we're going to do now is we're going to go and take those two leads that we were just looking at, the inverting and the non-inverting, and we're going to go and reference them. And that's all we would be doing over here, is where we would go and say, look, we're going to go and take this lead, we're going to tie this lead to chassis, or to my 0 volts. Which means that in reference to that 0 volts, if I take in any value of voltage along my inverting, that inverting is going to go and say in reference to that 0 volts, this is seen as being a positive value of voltage, so it's going to multiply it by a negative gain, because we got this over here, which means that it is going to go and switch from the negative out. It's going to drop my total amount of output. Same with this other one down here on the bottom. We just take a look and we say, well, we are going to go and reference now this one over here. So at 0 volts, that one is tied in at 0 volts. And then if I take a look at my signal coming in, my signal coming in is going positive and it's going on the non-inverting. So I'm going to multiply it by a positive 200,000, my gain that I'm going to go and have, which means it's going to go and switch out to my output in a positive direction over here. All that we have to do is we got to look at which lead we are leading that signal in on, and then it is going to tell us whether this thing is going to switch and send us out a positive output or whether it's going to send out a negative output. All right, let's talk real quick about the packaging over here. Standard packaging is going to be dual inline packaging over here. 741 is going to be a common one. Now, most of you probably aren't going to deal with these as discrete individual op-amp components. However, some of you might, if you get into the world of automation and especially into instrumentation. Okay, so instrumentation is a separate red seal standard trade. It's not automation like what UFE has. That's not a trade at all. That's just kind of a course that you can go and take. But it's an actual red seal trade that you are going to be able to take that will go and allow you to take care of instruments and things like that. Power engineering and instrumentation both are very common, and they're going to go and use these things where you are oftentimes going to need to go and apply these. You're going to have to build your own circuits. This one over here is going to go and have a few more connections. This is going to be my positive value of voltage that I'm going to go and have here. This one over here is going to be my negative value of voltage that I'm going to go and have over here. And then this is going to be my inverting lead, and this is going to be my non-inverting lead that I'm going to have here. And then this is going to be my output right over there. What you see is that we're not utilizing even all of the components off here. We're only going to go and utilize a grand total of 5 of these for this individual situation over here. The other ones are just going to get tied down to ground, or in some cases they're going to get tied high if we've got other options that are going to be able to be enabled on those chips. Very small little package. Inside that package we have got this, as we talked about before. Once again, going over this, take a look again. Here's my positive voltage, here's my negative voltage, here's my output, and in between the positive, it is going to drive through like that. It's just going to turn that transistor on. And from the negative, it would drive through like that to turn that transistor on. It's going to be an either or, never both simultaneously. And the rest of this section over here, all of this is going to be used to go and build my voltmeter section, where I'm going to go and have inverting input and non-inverting input that are going to take these in over here. Don't worry about the offset null control and things like that. That's going to be stuff that you would use if you ever get far enough down that road. You're going to have to learn a little bit more. We're just going to kind of scratch the surface what they are right now. But that would be used for tuning these when you actually go and put them into place. Those are going to be my older ones. You will occasionally find these ones as well, where it's going to be a TO5 type. TO5 type is going to just be a metal case rather than the plastic case. They stand off a little bit further. We'll give ourselves a couple of values of a couple more leads off of these ones over here. We're going to have inverting, non-inverting, and then we're going to have our output out of that one like that as well. Just a different type of CAN case that we are going to go and have. And the very last one to talk about here is going to be my flat pack, or my SOIC, small outline integrated circuit. These things are becoming very prevalent out there. The reason that these are so popular compared to my dual inline package is that my dual inline package has got pins that go all the way through. These over here are surface mount, which means that my board, I'll just draw this green line, you can think of that as being the circuit board. I'm going to be able to go and have on the top side of the board a whole pile of solder traces that are going to connect components, and on the other side I can go and place more components. I can have more components, and provided that those components on the other side are going to use the same type, we refer to these as gull wing leads, then we're going to be able to utilize the other side of the board. It just makes for a more compact set of electronics when you can utilize both sides simultaneously. Okay. Next thing that we're going to talk about is going to be open versus closed loop off of these things. A closed loop is where I'm going to go and have feedback. And feedback is really, really good because it tells me how far I am. You know, it would be like if you were trying to drive open loop versus closed loop. Open loop, you would really have only two things: going and stopping. You know, full power or full braking would be what you are going to go and have. Closed loop would allow you to go and adjust that throttle the way that you do inside of a vehicle normally, because you're able to take in your surroundings. You know, we can all do this. We can measure depth with our eyes, and we say, coming up, you know, really quickly towards that brick wall, maybe I should slow down, etc. Open loop, we're going to have extremely high values of gain, but it's going to be unstable. By unstable, it just means that it's just going to be twitchy. You know, we go a tiny little bit into the positive, and boom, we're going to go and drive this thing all the way into the positive. We go a tiny little bit into the negative, and we'll drive it all the way into the negative. This can be very, very useful for us if we have got certain components that we want to be able to go and drive, you know, high or drive low. We're going to take a look at creating some square waves out of some of these here in a little bit. But in a lot of cases, we don't necessarily want to go and drive it all the way to the positive value of voltage or over to the negative value of voltage. We want to be able to change from one to the other. In those cases, we are going to go and use closed loop. And closed loop, we are going to go and have a more stable one, but one that we can adjust. Let's take a look first at the op-amp as a differential amplifier over here. Let's talk about the op-amp as a differential amplifier. As a differential amplifier, we are going to be looking at the difference that we are going to go and have between two different leads on the inputs over here. What you'll notice is that we don't have any one of my leads that's going to be attached down to chassis or to common. So that means that I'm going to just be measuring voltmeter 1 and voltmeter 2 against each other, and then I am going to go and take the difference. Whatever the difference is going to go and be, I am going to go and multiply that by whatever my amplification is. This AOL, amplification open loop, is going to be what it is. Anybody remember AOL that used to send you CDs in the mail? I don't know, it's probably dating you, whatever. Back in the early days of the internet, AOL used to go and mail out CDs all the time, and they'd be like, put the CD in and get free internet, Explorer. You couldn't do it over the web. Completely not related to this, though. Going back to this over here, AOL is going to be my amplification open loop, and all I'm going to do is I'm going to find the difference between my volts. If this one over here is at 8.1, and if this one over here is at 8.2, I'm going to go and see the difference between those two, and then it is going to go and send that difference by my amplification. Now, if I'm going 200,000 times, that means I've got 0.1 of a volt multiplied by 200,000, which would mean that it is going to try to go all the way up to 20,000 volts. In reality, once again, we're talking about this thing as if it had a bank account. That's what it wants to do. It's going to be limited instead by what it actually has available on my negative and on my positive voltage leads that are going to be here. We're going to go and use these things in a lot of cases where we're doing monitoring. A great example of this would be, if I was checking battery cells, if I had a very large set of industrial power inverter cells where we're going to go and, take power, we're going to go and stick it onto a DC bus, and then I need to go and maintain these cells that I've got an emergency ride through. What you want to do is you want to go and monitor and make sure all these cells are going to be the same, because if some of them are at too high of a value of voltage or too low or they get unstable, remember what happens from when we were looking at rectifiers. If the voltage is different, then I'm going to go and have my larger one that's going to drive my current through the smaller one. And so what we'll do is we will go and use the differential amplifier to go and either apply more power to the one that needs to have it, or sound an alarm, disconnect them from the circuit, etc. There's all sorts of stuff I can do with that signal, but all I'm going to be looking for is what that signal actually is going to go and be. It's always going to be my non-inverting minus my inverting one that I'm going to go and have. So what I would have over here, let's say that this one was my 8.1 minus my 8.2. That would be a negative 0.2 difference, right? 8.1 minus 8.2 would be a negative 0.1 would be what those two work out to be. Multiply that by 200,000, and we'd see that this thing would try to go and switch out to a negative value. So it would be trying to drive this current over here. Whereas if they were reversed, my voltmeter 1 was 8.2 and my voltmeter 2 was 8.1, we would get out a positive 0.1, which would mean that it would go to this one. So what we can really do is we can use it to go and get a signal that's going to be associated with voltage values. Chemical processing, same thing. You know, if you got multiple cells, you're working with a membrane, you're separating chemicals and stuff like that, electrochemical processing through a lot of our, industries, petroleum industries and manufacturing, etc. You're going to need to go and monitor cell voltages as well. And so you're going to do it with, beefed up versions of these devices. Okay. Next thing that we're going to talk about is going to be the comparator. The comparator is going to be similar to the differential, only instead of us having two values of voltage, we're going to go and fix one value of voltage. It could be fixed at a value that is going to be ground, like this, or I could fix it at any other reference value of voltage. If I wanted to, I could go and reference this thing instead of at that ground signal. I could go and say that this thing is going to be attached to a plus 5 volts. And so it's going to go and then measure everything in reference to that plus 5 volts. What we would do with this one is, once again, we would go and send out a signal for, these things based upon what would be happening inside here. We'll go back to this one over here. They've got comparators in action. They're going to go and say, what would happen if we get a value of voltage in. The value of voltage in is just going to go, we'll take this over here. If I've got 1 volt, will that 1 volt be higher than ground? Absolutely will be higher than ground, which means that 1 volt multiplied by, because this is open loop over here, 200,000 means that it wants to go and stick out 200,000. Let's just give them a little dream bubble. That's what it wants to go and do, is put out that 200,000. But in practicality, it is not going to be able to put out the 200,000. Instead, it has to go and switch out to whatever I have here, which is 12 volts at this point. But then we've got a couple of drops inside, so we're going to go and have 1 to 2 volts less. We're looking at, maybe 10-ish volts that we are going to go and get out on our output. This one over here is the same deal, except it's going to be an inverting. Once again, if I put 1 volt in here, it is then going to go and take that 1 volt, and it is going to go multiply it by negative 200,000, because it's coming in on the inverting. So negative 200,000 times 1 means that this thing would want to go and put out, once again, it's got big dreams, negative 200,000 volts, but it is limited by what it actually has. Here's its bank account. It's got 12 volts. And so it is going to have to switch that out and lose a little bit of voltage drop on the way, leaving it at only 10 volts. Okay, let's take a look at it in action over here. They're showing us a comparator circuit over here where I'm going to go and have a reference value of voltage that I'm going to be able to go and adjust. And then I'm going to go and take in a feedback. So over here now, instead of this being at a value of 0 volts, they've got this thing at a value of voltage that I can go and adjust. They do have we're still going to go and have our plus value of voltage. I want to draw that in because it makes it clear, and our negative value of voltage that are going to be attached over here. And so now all we'll do is we're going to go and monitor these values that we are going to go and have over here. First of all, we're going to go and give this thing a inverting and a non-inverting input, because we would need to go and have that. Now that we've got this thing as a non-inverting, we take a look and we see that our feedback value of voltage, which could be coming from a tack or anything else like that, that feedback value of voltage is coming into the non-inverting. Which means that if it is smaller than my reference, let's say our reference is going to be at 5 volts. So if it's smaller than my reference, it would be a negative, let's say it's 4 volts that we have over here. 4 volts coming in. Compared to that, this thing is then going to go and look at that. It's going to say, oh, we've got negative 1 volt in reference to this, right? So we'll look at that as a reference. So in reference to the 5 volts, 4 volts is negative 1 volt. Therefore, it is going to go and switch to a negative. So it's going to just drive that one over there to a negative. And if I have got that driven to a negative, will this relay be on if that would be attached to negative or to ground? Probably not, if this is going to be the same negative value as here. However, if I go and bring this value of voltage up, let's take this value now to plus 6 volts over here. So I'm getting 6 volts from my feedback, my TAC. EG is equal to VLV, which probably means that we're going faster. That 6 volts is going to be seen as being plus 1 volt in reference to this 5 volt. Remember, that's what it's comparing it against. So plus 1 volt in reference to that. The little voltmeter inside of here is reading plus 1. The little ELF is then going to go and throw the switch, connecting this thing to the positive, because it's going to be a positive value. And at that point, we would go and have a full value of voltage that would happen across here, and then this thing would go and operate whatever we have for that relay. It could be applying brakes or something like that if we're spinning this thing up too fast. Last one that we're going to talk about for this is going to be using an op-amp to square a sine wave. This is a lovely thing because these things drive so incredibly rapidly into full saturation. What we are going to do is almost the exact second that we cross over top of this axis over here, it is going to go and see that it's going to be a bit more positive than this. This is going to be at my 0 volts, which is going to be the same as my neutral. Remember, we ground the neutral there as well. So we're going to have that at 0 volts. That 0 volts we have over here, the second we go a little bit positive, and we see we are coming into the non-inverting. We go a little bit positive, therefore it is going to switch almost instantly. Because we've got that 200,000 gain, it is going to go and drive hard and fast into the positive. So there's going to be a tiny, tiny little lag over there. That's going to be just a small horizontal line, so a tiny little line, then it goes and drives all the way up, and then it is going to stay high until it gets down below here, and then all of a sudden it's going to go and drop down, then there'll be a tiny, tiny little line, and then it'll go down into the negative. It's not quite a perfect, rise, fall, rise like that. What it has is in actuality is it's a tiny little bit, and then it is going to go up, and then it's going to drop down, that's going to go tiny bit, and then it's going to go down, etc. So for a couple of tiny, we're talking microseconds, if not nanoseconds, we're going to be hovering at that 0 volts, where it's neither putting out a positive nor a negative because it's not high enough to drive that out. But it's going to be really, really, really tiny. If you actually go through all the math for these ones here, you can use those formulas for like E instantaneous, which is, I don't know if you guys remember that one there, but small e is going to be my E peak times sine theta of what we are going to go and have. What we would be able to do is we would be able to take a peak value, if this is 120 volts, take it up to a peak of 170. You can then go and figure out how many degrees in this thing would actually switch. By the time you go through all the math, and I'm not going to do it here right now because you don't need to see all the math, you can solve it yourself at this point. But if you go through it, it would be 0.00002 of a degree in is where this thing is going to go and trigger and drive higher. Remember, this is over 360 degrees. This over here, if I go and divide this down, is going to be at 20 micro degrees, or 21 millionths of a degree is where this thing is going to trigger to go high. So it's, as far as we're concerned, a instantaneous reaction that we are going to go and get out of these. Okay, that's going to go and be the op amps that we are going to go and have. And so we are going to just leave that one now. We're going to go and look at our calculations next.